Swayam Prabha. Digital India. Educated India.
What happens to the system when we sample the system. So all we know from our analysis, our practical implementation, that we are doing the sampling. We are doing these three steps. Okay, reading the sensors, then computing the control, and then third one is implementing to the actuator. Okay, this we are doing again and again in some kind of a sampled kind of a manner. Now then the fundamental question comes, is what happens to the signal when I sample the signal? Okay, that is the first question. Okay, so we'll now see these questions in more details. So schematically something of this sort is happening in our system. Okay, so you have a your plant here, which is your some mechanical system, which is inertia or something, which is actuated by some actuator, some kind of a motor or something. So in your case, your motor case, you'll have a disc as a plant, and your motor as an actuator, or motor inertia plus disc inertia as a plant, and then the magnetics going on in the motor as an actuator. Like that, one can visualize in some sense. Then encoder is getting your feedback as a sensor, and then you're sampling. Now here we don't have A to D here. We just have a encoder interface to do this get this reading of the encoder directly into your microcontroller. And then we don't have even digital analog interface. We have this PWM interface here to actuate your actuators. So this loop is continuously getting executed. Every sampling time you read your sensor here, then you process that in your control computation, and then you implement it on actuator. Again you read further, and keep on doing that in an infinite loop, so to say. That's how your actual control will happen in any of the systems. Now the question is, because we are implementing something, so this activity happens in the digital domain. So once it is implemented at say whatever sampling, some instant, this actuator or your PWM duty cycle has got updated. Okay, and from that update to now, all these things completion, all these other activities happening with one sampling time completion, and again it is updated. There is a lag of, or there is a delay, or there is a time lapse of one sample time. Okay, so now the way this would happen for my system is, I would let me sketch it here. I would see the system would see some sort of let me get a new page here. So I would see some kind of a my control input is if I see, just plot the control input as a part of as a function of time. Okay, so this is my first sampling time, this is second sampling time, this is third sampling time, and so on. So I have first duty cycle coming up here. Okay, up to this point, then it will get updated and it will become something here, and now over two sampling instances it's going to remain constant. That is a important thing here. So 0 to t, it has some value here. Okay, then from t to 2t, okay, there is other value. Okay, this is how is control going on my system. So the next question comes, okay, if my system is receiving these inputs in this kind of a successive steps kind of a thing. Okay, so it is receiving these kind of successive steps, keep on receiving like that kind of input. How my system is going to respond to this kind of input. Okay, so that is a question that is addressed, for example, when we talk about this digitization or like digital control kind of consideration. Normally what we do is we just implement control, we develop some controller in analog domain, and we say, okay, oh look, with enough fast sampling time, I would be able to kind of implement it faithfully in a digital domain. Fine, and then our kind of like job is finished. And okay, we say that okay, I have enough sampling, fast sampling, so that this controller will behave as if it is continuous system. Fair enough. Okay, that is also a good argument to kind of go. Many times people use that, and they don't bother about getting into digital analysis itself. But we need to be aware as a so there's we as a mechatronics engineer need to be aware that okay, at some point I may not have that flexibility of having kind of a control possibility. So fast implementation possibility is not there, that as if this system will be considered continuous. Okay, under that situation, we need this analysis of digitization. So we'll have these two parts coming up. One is your sensor. Typically, in our case, it is anyway a digital sensor, but analog sensors will have this issue that okay, you sample this sensor signal. Okay, so sensor is read again every sampling time. Actuator is given input every sampling time. So when the sensor is read every sampling time, now I need to know that okay, if whatever samples that I am getting from the sensor are representative of the signal that I want. Okay, so what happens to the sensor signal when I sample it? That is another kind of a mathematical question that one can have. So first question is what happens to my system when the input is in this kind of a steppy form, and other question is okay, what happens to my signal when I sample it? So when I receive the samples of the signal, how do I see them representing my signal well or not or whatever? Okay, so there are these other kind of issues. So some practical issues are there, but some of them are related to sampling. Say for example, if you maybe this will become more apparent when we start looking at sampling. So basic idea here is to see as a continuous domain signal. Okay, is now represented as samples in the digital domain. Okay, so you have this signal which is continuous in nature. So let's come back again to our schematics here. So now here we are considering for the sampling, we are considering a question where you have this signal. Okay. Oops. So this signal, I have some signal. Okay. This is a f of t, continuous domain function of time. Okay, this is my time here, and I take these samples of the signal. I sample this signal at say some sampling rate. Okay, so this is t, 2t. The samples are coming at these different times. Okay. So if I represent this signal only in terms of these discrete points instead of this continuous, because in computer I cannot represent continuous signal. I always will have only these discrete data points which are coming in some kind of a form of an array. So if I represent signal in this kind of a sample form, what is that I'm missing, and how these samples are representing my original signal, how faithfully? Those are the kind of questions that come up mathematically actually. So another thing, this signal has some kind of a frequency. So we need to be familiar with something called frequency content of the signal. So you have learned Fourier transforms in mathematics. Okay, so if I take a Fourier transform of some signal, okay, so the signal will have frequency contents up to some certain frequency, say omega 1 here. Okay, so now what I'm having here is f of j omega. If you recall your Fourier transform, this is a magnitude of f of j omega. Okay, um, so this will have some magnitude, like some variation up to this omega 1. Okay, now just to kind of give you some sense, if your signal is sinusoidal, oops, what happened? If your signal is sinusoidal of say frequency omega 1, then you think, okay, what will be your this f of j omega is going to look like. Okay, so f of j omega for f of t, so let's call this f1, some f1 is sine omega t, omega 0t, let's say. Okay, so if you recall your Fourier transforms, you'll find that it will have some kind of an impulse representation here at frequency omega 0. Okay, so we may need a little bit of a refreshing of your Fourier transforms to really understand in really get great depth, or you can just have a feel for, like, say, okay, look, my signal has, say, signal sinusoidal frequency, single frequency omega 0. In the frequency domain, I'm not going to see anything other than omega 0. That's the kind of a physical sense you can have. So if the signal has two frequencies, omega 0 and omega 01, okay, then in the thing I'll see there's two peaks here. Okay, instead of just one peak omega 0, I'll have another peak at omega 01, something like that. So like that, I can see my signal to be having these multiple kind of frequencies depending upon what is the nature of a signal. Okay, so that is little bit from the physics perspective, and then to kind of get to precise how this comes, you need to kind of invoke mathematics of Fourier transform. Okay, if you use the Fourier transform formula, then like you'll start like getting the similar kind of results. Okay, and for a signal, there are techniques by which, like, you can numerically take Fourier transform. Okay, it's called discrete time Fourier transform. Okay, so for that numerical Fourier transform, there are this very efficient algorithm called FFT algorithm. Okay, so this is a algorithm called FFT. Okay, fast Fourier transform. Okay, so if you see in MATLAB also, you'll have this command called FFT. So you can use that command and, like, see how it kind of given a signal. So I give a signal like this, and I fed in these discrete points of the sample points of that signal with some we know what is the sampling frequency, and you feed them into this function in certain kind of a way, and this MATLAB can give you this the FFT plot, okay, or this frequency domain representation of the signal. So you can get actually this kind of a signal, and typically all the signals that we consider in the mechanical domain will have some kind of a limit with this omega 1 here. Okay, so you'll have this signal which are limited in frequency. They are not like, you cannot have a signal which is having infinitely, like, many, I mean, the frequency contents. Okay, frequency contents will be limited to by a certain higher frequency, because mechanical elements in the system cannot move faster than certain speed. Okay, so this is what we will consider mostly for signal analysis, that okay, our signal is band limited. It's called like some band limited in terms of some jargons actually. Okay, so this band limited signal by omega 1 frequency, and then we represent this signal in either time domain or in the frequency domain, and we should be able to go back and forth in time and frequency domain. That's what would happen based on the Fourier transforms. We'll use Fourier transform analysis to do that. Okay. Now the questions are like, are the samples true representation of original signal? Okay, so further question will be, if it is true representation, then can it be possible to completely recover the original signal from its samples? Okay, what is the role that sampling time or the sampling frequency has to play in this business of getting the recovery of entire signal done? Now. This is another question that we have said, okay, PWM which is going to the motor as a sampled signal. So what is the effect of, like, is there some sampled input going to the, in a steppy form, it is going to my system, what is its effect on the system dynamics? Okay, so many times, like, you will find, like, the discrepancies that are coming in actual practical stuff and what you are getting in simulation would be because of this insufficient sampling, or sampling frequency is not proper. So we will get to this in little more details now. So yeah, we are doing fine in time. Okay, so first let's understand what is sampling. Okay, so and how this sampling can be visualized for simple kind of a cases. So you all might have I don't know, you might have observed some old movies, okay, with a horse cart kind of a thing, old really black and white kind of a movies. They used to have this kind of a film to record the movie, and then they replay the film to play the movie. Okay, there is no kind of a digital camera for like recording videos and things like that. Okay, so this is like a film based recording of the movie. And if you observe there, like suppose there is a say typically this horse cart is moving in the forward direction, but then the wheels will appear to be moving in the opposite direction. Okay, and that's very funny. I mean, when I was a child, I was wondered, like, okay, why such things are happening there, and then you might have seen, like, your fan is running. I don't know, now there are tube lights which are having flicker. There are tube lights which flicker. Okay, when they're flickering, like under flicker, like, the fan will appear to be moving in some different direction. Okay, those kind of effects basically. So you have a stroboscope nowadays, like, even mobiles have these apps which can give you stroboscopic kind of effect. I might have one. Yeah. So yeah, so this is like, where I can set like some frequency, and I can start producing this kind of a stroboscopic signal here. Okay, so now I can flash the signal against some kind of a object which is moving, and it will freeze the images at the time the light is flashed on the surface. And if the frequency of motion and frequency of the strobing matches, then even that moving or vibrating object will look like it is stationary. Okay, those kind of effects are all like related to this sampling. Okay. For example, if you see this cart example, like I take, say this is moving in the forward direction. Okay, and like look at this pointer. Right now it is pointing this. Now it rotates actually a complete rotation and comes in this position in the second part that is shown here. Okay, sorry, let me get my mouse. So here if I take second image, and here I take, like, it's the same speed, it is moving forward, and again it completes one rotation with little less kind of degrees, and I take third snap, and now I replay the snaps. What will appear is to kind of like these to be moving in the opposite direction. Okay, the wheel will start moving in the opposite direction, and this is called aliasing of the signal. This like some kind of a loss that is in the signal. So I have lost a direction of motion, and I have lost, like, the speed also here. Okay, so the speed actually is so fast, but now I'm getting, like, some signal which is now visualizing. It is very slow speed, but and also it in the opposite direction. Okay, so this is called aliasing of the signal. Okay, so your signal is lost here. Okay, now the question is, can we quantify this effect? Okay, so one can see now that, okay, if this phenomena is happening, like the pointer moves from here just to like up to this point, no problem. Up to this point, I'm talking of now like only the one successive cycle. So from here it is moving here, no problem. 90-degree motion, no problem. If it like again further down here, there is no problem. Okay, it comes here, I'll have some issues coming up. You see that this pointer going from here, and like I take next snap when it is like vertically down position, then like I'm on the verge of like losing something. Okay, if I go here, then I have already lost that. Okay, because now it will appear that I'll move like in this direction. Okay, so you can see that there is also sense of that kind of speed of sampling needs to be like, say wheel has some RPM, okay, or frequency omega for motion omega 0, let us say. And if I sample like 2 samples per second per cycle, okay, for this one cycle I take 2 samples, then I'll have one pointer here and other pointer say here. I'll have some kind of a lossy thing. But if I take uh, now for if I take more than 2, okay, then I'll immediately start seeing that, okay, this comes. So what we are talking about is like the number of frames, okay, per revolution. Okay, we are not talking in terms of the time here, okay, not per second kind of a thing. Okay, so you don't get confused. So for with one revolution, if I have say if the pointer comes here, that means in one revolution I'm taking 1, 2, 3 and 4 samples. Okay, 4 samples. I begin here, 1, 2, 3, 4. 4 samples I'll take if I have 90-degree motion happening here. That is a kind of a sense. So one can always transfer that in terms of the time with considering the frequency of motion to be omega 0. Okay, so if my frequency of sampling is 2 omega 0, okay, 2 times, that means I'm taking 2 samples, okay, in one rotation, then the possibility can be only like this sample and other sample is 90-degree. Then I'm in some confused state. Okay, if it is like more than 2, I'm on this side, then it is like I'm safe. I can still determine. And if I'm on other side, then also I can say I'm like confused completely, that okay, this is less than 2, so I'll have one sample here and next sample may be coming up here on here. So then again I'll have a loss of data. Okay, so from that perspective one can see that the frequency of sampling, if it is more than 2 or less than 2 or equal to 2, you'll have a different kind of interpretations of like the sample signal coming up. This is like a more like a physics here. Yeah.
Sir,
Yeah.
for less than 2 also,
Hmm.
if it is less than 1,
Uh,
then I think we can still get the direction right.
so if it is less than 1, so
I
you
mean,
have one sample here and next
yeah.
sample coming up here, say for example. How can
No,
we
no,
get a direction right?
it is towards the right of the first sample,
So first sample is
which
here.
means after
It
one
is.
rotation, after some time, so one rotation plus some delta t,
Uh,
I'm getting it again,
uh.
which means
Okay, so
there's a
then
lot of delay,
that
but
is
still,
so yeah, that is correct. But so what we are talking about then, like no, loss of we are talking of this loss not only of the direction. So I'm giving this example for direction loss, but like no, in that case you would have a speed loss. You'll have like no, one complete cycle is lost already. The speed has lost so much there. Okay, so this is like that's what we call it a harmonic. Okay, so you have one complete cycle has passed, and then like no next cycle may forward direction you have started measuring perfectly fine, you are getting the direction sense right then, but still there is a loss of the, it's not like no the original data, right? It is I have lost so much of so many samples in between, or like so much of a data in the sense I don't know now the speed that is I'm getting is correct or not. Okay, I'm definitely do not have correct speed there. Okay, so this is just to kind of give you a feel of what is happening when we can do like a lot of mathematics about it, that follows. But if you have this understanding good here, then you can see that okay, look, even with samples little less little larger than 2 omega 0 frequency, I still have a chance to kind of get my reconstruction or signal represented completely. Okay, so that we'll see how mathematically it can come up a little later. Okay, how are we doing time? Okay, we have still 10 minutes to go. Good. Okay, so now how do we quantify some stuff like so if I give you these frequencies, you may be able to come up with these what is the speed that I'm going to see actually by doing this such kind of analysis that we are talking right now. But are there any other kind of a formal ways of doing this, or seeing this in terms of the signals eventually? That's what we'll see. For example, now if this is a sinusoidal signal, okay, for that sinusoidal signal, if I'm sampling at certain frequency, okay, which is now, so this is one period here, okay, so same thing that is happening here, I'm now representing it in terms of the period. So this is one cycle is one period, okay, so this one cycle is corresponding to this one period here. So now I'm considering it like a vibrating object, for example. So to say, if you want to connect to the physics, it's like a vibrating object, and what are these points that are just like a snapshots that I'm taking when I do the stroboscopic kind of a measurement on that vibrating object. That is a kind of a sense if you want to kind of understand this in terms of some kind of a physics associated with this. But I mean, in general, this is now exactly what is precisely will be happening when we start taking a signal and we sample it. Okay, so one can see that sense in terms of physics by using a vibrating kind of a object, and these are the points where you have a stroboscope applied to that. Okay, so if you see now, these are the equi-space points, but which are beyond this 180 degree phase. Okay, so this is like total 360 degree. This is 180 degree up here, and beyond that, I'm kind of putting somewhere first sample, and now equi-spaced other samples. And if I start plotting them, I'll see there's some other sinusoid is emerging out of this. So I'll see the speed of actually the speed of vibration was this, or speed of oscillation or frequency of the signal was this, and what I'm seeing actually the frequency of sample signal is much lesser there. Okay, so original sine wave is completely lost here. We are not representing original sine wave in this kind of a sample scenario. Okay, so under what conditions we can see our original sine wave? So if I say okay, my first sample is here, next sample is exactly at 180 degree, then all the samples will be a straight line here. Okay, that's complete loss of that is also not some kind of a correct representation of the signal. But if I have some sample here, next sample is somewhere here, and then so on and so forth, coming other samples follow, then I apparently see the signal to be somewhat kind of not really sinusoidal, but by using those samples I can now generate original signal back. Okay, based on my arguments that okay, look, from that wheel I can see that okay, if I'm taking this sample which is less than 180 degree rotation for the wheel, or less than 180 degree phase for the signal, I'll be able to kind of reconstruct, I'll be able to kind of see my contents or original sense of that signal along with the direction and the frequency or speed that entirely is preserved. So how do we quantify that? So that's where we start now looking at the theorems for doing that. Okay, now again here we will not have much time, or will not have time at all probably, to get into the proofs of these theorems. Okay, so we are trying to kind of understand these theorems and apply. Okay, so we are into that kind of a phase. The proofs of this theorem will follow by two parts here. Like, one is like you need to have a understanding about the Fourier series, and other is understanding about Fourier transforms. And third thing maybe about this direct delta function. Okay, so these three are like some base mathematical background requirements to get to the proofs. Okay, so the idea here is that now, as we have seen, say some signal f of t is there, and as we saw, like all the signals, mechanical domain, or like these mechatronic signals will have this limit of the band. Okay, so we don't know what is there in between these 2 points, or here from 0 to this omega 0, what is there. We are just kind of like trying to represent it somewhat by this kind of a straight line, but this is not a thing that is the actual representation of a signal. Huh? This is just to kind of show that okay, your signal exists between like this to this frequency. Okay, so typically you give this f, and like you say that okay, it is a band limited signal, and then you construct this kind of a some kind of a representative of that band limited signal. Okay, so this means like this signal is band limited by this omega 0 frequency. So this may not be linear variation. It may have some kind of a very skewed variation in this domain, but nothing would exist beyond omega 0. No content for f of j omega would exist beyond omega 0. Okay, there will be always 0. Okay, so this is how like we consider the band limited signal. What it means is the fastness of the signal is not more than omega 0. It can only be fast as omega 0 kind of a frequency. That's it. Beyond that, it doesn't have anything which will kind of have the faster variation than that kind of a speed. Okay, and this is very important concept for signal representation in time domain to frequency domain, so that we can see the different aspect of the signal better in the frequency domain. Okay, say for example that the signal has band limit of omega 0. This aspect will not come by just seeing the signal in time domain at all. Okay, you see some variation in time domain, how do you know like okay the signal has no frequency contents more than omega 0? Okay, that is not very apparently coming in the time domain. So that's why we have this different mathematical representation of the signal from time domain to frequency domain and so on and so forth. Okay, so if you see the actual signal, I'll show you some actual signal. Actually, we can see its transform here. See, this is the actual signal in time domain. Okay, so this is a time per second, actually recorded from our own kind of a strain gauge measurement for a beam which is vibrating. Okay, so this is the strain gauge is at the bottom of the beam, and the beam is vibrating. So you can see that okay, this has some kind of a by seeing the signal, how would you kind of know? Okay, you say okay, some frequency, base frequency is there, and some additional frequencies are there, but we only can see that. We don't know whether this will be having some kind of a band limit, or it is having what kind of frequencies contained in the signal. Okay, for actual signal. So that's where like this FFT of the signal is very, very handy. So what it shows here is like around 12 hertz we have one frequency coming up, and then there is some other kind of a component of frequency which is coming up around 34 kind of a hertz frequency. So these are actually two modes of vibration of a cantilever beam. Okay, the first mode is here and second mode is here. Okay, and then there are these small noisy components are there. Okay, so these are kind of safely ignored. You just need to kind of see where are the major peaks for the FFT kind of a signal. Okay, so beyond this now there is no other frequency coming up as at least in this kind of a signal, which has excitation given to some extent because of which it is having this kind of a response. And in this response now the signal is band limited to say this frequency up to say 35, for example. Okay, like that one can see the actual signal in the similar way as we have seen this. So you can see that the signal is no way like this triangular kind of a representation at all. Okay, and for the sake of mathematical completeness, you actually define this on the other side also. Okay, so we not get into more kind of when you get into proofs, like you'll see that okay, this part is actually needed to be considered. Okay, so that is coming mainly from the mathematical kind of precision of discussion. It has this part has no real physical kind of significance. What is a negative frequency will not have a physical significance at all, but for mathematical completeness it needs to be considered. When you do like further analysis, then this will start using on the other side what is happening. Okay, so now I would leave you with this question that okay, if my sample this signal, okay, to represent just this kind of a sample points, okay, what will happen to the signal in the frequency domain? That is a key question. How do we see that? Okay, how do we see the sample signal appearing in the frequency domain? That
So
is
it will
what we'll
be
yeah.
cut off in the frequency domain, maybe
No,
at 1 by
no.
okay.
At some point it will be cut here. No, so that's where like no we have to see when these are the samples seen in the time domain. Okay, what is that you will see in the frequency domain is given that when this is a continuous signal, the frequency domain signal looks like this as a frequency content of that continuous signal. Now, when sampled, what is going to happen is a question. Okay, and when you say, so see, normally we have a notion that okay, oh, something is sampled here, it will be sampled in the frequency domain as well. No, that's not correct notion. Okay, that's what we need to kind of wash out that kind of a notion that okay, if something is sampled in the time domain doesn't mean that in the frequency domain also there will be some samples that okay, you'll see only this kind of a samples here. No, that is not true. Okay, so what happens we'll with this mathematical analysis is this, we'll see what is this interpretation maybe in the next class, but maybe I'll post these slides. You can try to kind of see up to this point maybe to guess okay what is happening here. It's not trivial to kind of guess that, but see if you can give some kind of a thought to that. Based on whatever your knowledge about Fourier transforms and things, you can apply that to such a signal which is represented as a discrete kind of a sample. So see this Fs is a mathematical representation of the samples of the signal. Okay, they are represented as summation of all these direct delta functions which are coming up at each of the sampling time. Okay, so we need not get into all these details, but we certainly need to understand what happens here. Okay, by doing this mathematical analysis, what is final conclusion is what we need to be very careful about to understand it and apply it to some situations. Okay, that is what we'll do from the next class. Okay,
So what
so
does frequency even mean in a discrete sampling setting? For a continuous signal, I can think as summation of sine terms.
uh,
So they will each have
so
an omega.
right. So for a continuous signal, you have the same way you can say, okay, if I need to represent the signal, say for example, by using, so I would give you some kind of a sense of thinking. Okay, if this signal had been a periodic signal. Okay, let's say this signal is a periodic signal. What you would think? You would think in terms of representation of periodic signal in terms of Fourier series. Okay, and in the Fourier series, the coefficients of Fourier series would give you contents of the signal at each of the Fourier components. Okay, these are sine and cosine components there, right? So each of the frequencies, how much is that signal contributing to is what I am getting in the Fourier coefficient. So this is like a Fourier coefficients that you are plotting here. So you have a continuous signal here, okay, or periodic signal here, okay. But when you see the Fourier coefficients come as a discrete here, okay. Now, when I say in the limit that my period of the signal goes to infinity, okay, then this becomes like a continuous signal, okay, and that time this instead of these discrete parts, I get also this kind of a continuous domain here, continuous representation here, okay. So that is a kind of a sense one can think about, okay. So this Fourier transform is nothing but like, you know, the Fourier series in the limit as period of the Fourier series goes to you know, the period of the signal goes to infinity. So this is now this period is infinity means this is not periodic signal, okay. So non-periodic signal will have this infinity period, okay. And for that signal, so that is a kind of a sense we can see for the Fourier transform that is happening. Now if I say in the similar kind of a way, like, you know, if I need to represent these multiple kind of a, you know, peaks that are like coming as these direct data kind of a functions here, how can I represent them by using a Fourier series? That is a kind of a way we start thinking, and we'll get some kind of answers there.